penalty. How is it going?
It's going.
It's going. All right, so hopefully everybody turned in something for PA4. I'm missing about a quarter of the submissions.
You're missing about a quarter?
Yeah.
Oh, no.
But I think that's partially people who are deliberately planning to turn it in a day late to have more time to work on it, or other things. So hopefully if you think you turned it in, you did. And if I did not get it by, I think it was like 8:30 this morning, I sent an email on Canvas to each person for whom I was missing. So if you didn't get an email from me saying that PA4 is missing, you're good. It means I got something at least. So questions?
How do you purposefully not turn these in? Isn't that just like keeping your Git repository?
Well, so I don't know.
Okay.
I mean, if you're looking at your schedule and it's like, okay, I'm gonna need more time, I can turn it in today and it doesn't do anything, but I think if I turn it in by tomorrow, I can get, all of it working, then you might say, okay, I'll take the 25-point penalty and turn it in then. All right, no questions?
Is VI your main text editor?
Yeah. I'll use Kate sometimes.
I don't know what that one is.
It's like Notepad, but it works. And I'll use that sometimes if I want something up on my screen that I can easily like copy and paste from. But yeah, usually VI. All right, well, let's go on to PA5, because you've had 2 hours off now, so I know you're anxious for more stuff to do. So programming assignment 5. So this is the egg drop analysis program. We started talking about egg drops yesterday. So logistics first, and then we'll go through details. So this is a group project. Okay, you can work in groups of up to 3 people. It's totally up to you. You can work on it alone if you like, or you can work with a friend or 2 friends. Your choice. I'm not going to have you do presentations on this. Okay, last quarter for presentation for a group project 5, we had groups come up and present. I'd rather spend the class time going over more material, so I'll grade these myself. Submit via GitLab. Your GitLab repository is called egg test with that capitalization. And you need to upload it by the due date, which for this is Monday. So it's a week from this coming Monday, about 10 days from now. Okay, not 2 weeks from today, because that would be the last day of the quarter. So earlier due date, okay? But it's a group project, and it's one function you have to implement, which is this egg function. So it should be doable in that time frame. So your main file should be called eggtest.c, and you need to include a make file that creates an executable called eggtest, lowercase. All right. There's a sample of this under /temp on the server that you can use to check your answers. All right, and make sure one person submits to the GitLab repo by the due date. If multiple people submit, whichever one I find first is the one that I'll end up grading. So coordinate amongst your group members and make sure who's going to do the submission. And you can all use GitLab, just don't add me as a reporter unless that's the repo you want me to download, because I'll never see it if I'm not a reporter, so you can do what you like.
Can you just put the team members' names in the README?
Yeah, so I was just looking for where I talk about the README. Oh, there we go. Okay. So I want a README file named uppercase README. Okay, not .md, not .txt, just uppercase README. And in that file, you should tell me I worked alone on this, or I worked with the following people, and list the full Canvas name of everybody who was in the project. Okay, including yourself. And put in the names from Canvas. Don't just say Bob and Betty, okay? Canvas names so I can link it up. I would like in the repo your source code, the make file, and the readme file, and that's it. Just those three things. If you have multiple source files, that's fine. If you have .h files that are included, that's all considered source code, okay? But basically the pieces that you need to build the executable, the make file that says how do I make the executable, and then the one readme file. All right. Also for this one, I'm not taking any late submissions. Okay, it's due the last Monday of the quarter. The next day is SLP presentations. I'm grading those. I'm working on exams. It's not feasible for me to spend the next few days taking in late assignments and regrading and so on. So this is a hard deadline, okay? If you're in a group, you got 3 people, make sure at least one of you remembers to turn something in by the deadline, okay? Monday morning at 8, that's when I'm gonna download, and I'll only grade the stuff that I actually find. And again, you know, use Git, keep things in there anyway, and you've always got your latest work available. So let me just show you the sample program. It's not terribly informative. So egg test, how many floors? I don't know, 40 floors, how many eggs? 4 eggs, fewest number of drops is 6. That's all your program has to do, except it's got to come up with the right number. Okay, but this should be giving you the correct number based on the algorithm that we've talked about. And I'd like your program to be that simple. Okay, please don't clear the screen, don't print a lot of introduction, don't change the order of these things. Number of floors, number of eggs, and then print out the fewest number of drops required. Okay, and that is specified in here. So egg test should simply ask the user for the number of floors, ask the user for the number of the eggs, and then print the minimum guaranteed sufficient trials and exit. Okay, so keep it super simple. All right, so let's go through the egg drop algorithm again. We talked about this some yesterday. Let's go through it again with an eye on PA5. So you're dealing with a fundamental question, which I just call the question in this write-up. The question is, given F floors and E eggs, the question is, what's the highest floor from which you can drop an egg without it breaking? Okay, and all the simplifying assumptions, not all of which are spelled out in here, but if the egg survives from this floor, it'll survive from a lower floor. If it breaks from this floor, it'll break from higher floors. If it breaks, you can't reuse an egg. If it doesn't break, you can use that egg again, and it's not changed by the experiment you just ran. All the eggs are identical. Any time that you drop an egg from a given floor, the result's always going to be the same. Okay, it's not like one time suddenly the wind will shift and it'll hit differently and break. Okay, so the experiments are perfectly reproducible. So that's the question, what's the highest floor from which you can drop an egg and have it survive? And the goal of your program is to figure out, worst case, how many experiments do you need to answer this question? Okay. And it's a little bit of the best of the worst, right? You're trying to find the minimum guaranteed number of sufficient trials. Okay, you can always do this, you know, if you've got 50 floors, you can always do this with 1,000,000 trials, right? So 1,000,000 is not the answer you're looking for. Can you always do this with only 10 trials? Okay, if you can, and that's the best you can guarantee, then 10 is the answer. But if you can guarantee that you only need 7 trials to answer this question, then 7 would be your answer, unless there's a better guarantee you can make. But it's not just the best case, fewest number of trials that you might need, because you might get lucky and, you know, drop your egg from floor 8 and it survives, and then drop it from floor 9 and it breaks. 2 experiments, you got your answer. Okay? That's not the guaranteed fewest number of trials you need in general, though. So we want you to say, if you're really smart about this, and you know how many floors and eggs you have, tell me how many experiments you have to run. You might get the answer in fewer than that, but that's guaranteed to be enough, and you can't guarantee a better number. Okay? All right, so a few of the approaches that we talked about already, if you have as many eggs as you have floors, you can just drop one egg from each floor and tally up your results later and, you know, find out which was the critical floor. On the other extreme, if you only have a single egg, you've got to start from floor 1. Because if I start even from the second floor and drop an egg and it breaks, I cannot answer my question. I don't know if it would have survived from the first floor or not. And if I've only got one egg, that's the end of my experiments. So if you have a single egg, you have to start from floor 1 and work your way up until it breaks, or you hit the top floor and it survives. And then you have your answer. So the fewest number of trials you can guarantee would be sufficient in that case would be the number of floors. And in the in-between cases, it depends on what happens, whether the egg breaks or not. So to determine worst case, how many experiments must be run to answer the question. Unlike knapsack, we can't actually come up with an algorithm which says first try this floor, then try that floor, then try this other floor, because those choices depend on whether or not the egg survives. Okay, but we could unwrap that for a particular situation. All right, so here's your function. So your egg function takes two arguments, number of floors, number of eggs. And it returns one of the following four values: 0 if there's no floors, 1 if there's exactly one floor, floors if there's exactly one egg, and this funny recursive formula otherwise. This is the general case. So this expression right here is the result of dropping an egg from floor F and having that egg break. And this should be F minus 1, not floors minus 1. We'll see how many typos we find in the assignment this time. All right, so if you drop it from floor F and the egg cracks, you know the critical floor is somewhere between 1 and F minus 1. Okay, and your number of eggs is reduced by 1, so you can call the egg function on F minus 1 eggs minus 1. And that'll tell you how many trials you needed in that case. If the egg survived, then the critical floor is somewhere between F plus 1 and floors, you know, the top floor. And there are this many floors in that range, and you still have all of your eggs. So egg of floors minus F comma eggs will tell you how many trials you need in that case. Okay, we don't know if the egg's going to crack or survive, so whichever one of these two recursive calls gives the largest value, that's the value we have to use, in case you're unlucky. And then we add 1 to that because we also spent one trial dropping the egg from floor F. So this is the best guaranteed number of trials that are sufficient if we drop the egg from floor F. Okay, but for a question with this number of eggs and this number of floors, we can drop that first egg from any floor we want, from 1 up through floors. So we'll find this guaranteed best value for all possible first floors, and then we'll take the smallest of those. So that's where the min comes in. So this is the min over F ranging from 1 to floors. All right, does that make sense? All right, so repeated subcases, this will take a really long time if you don't have dynamic programming in there. So you want to make yourself an array for saving values. Okay, so make yourself a save array with 500 for each index. And the way I'm wiring this up, save bracket F bracket E is the stored value of eggs called with F and E as arguments. So we're only going to do this for up to 500 floors, 500 eggs. And so when you try to call this egg function, first thing you do, check this save array. This will initialize it to 0. And so if the value is equal to 0, call your egg function and then save the result in your save array. Otherwise, just return a value from the save array. All right, main program we talked about, submission we talked about, that's pretty much it. And this will blow up in some cases. Oh, maybe not. Maybe it won't blow up. Okay, and I won't test it for more than 500 floors or 500 eggs.
What if you do?
In this case, I'll definitely seg fault,
Okay.
right? Because I'm just blowing up my arrays, right? And I'm not going to test with weird values that aren't integers. So I'm not worried about your main program at all. I just want it as a way to exercise your egg function. So you can totally lowball scanning the arguments and so on. I was going to have you just give me the egg function and I would link it into my own program, but that gets into more issues for you about testing it. So just give me a basic main program. All right, questions about this? I don't need to know anything about your groups until you actually submit. Okay, so you don't have to ask me if I can work with so and so and such, but just 3 people per group or fewer, and set them up however you like. I'm not going to upload that new version until I do this a few more times and see if there's other errors in it. Because historically, there's bound to be. All right, good to go? All right, well, let me give you one more example of this kind of repeated substructure setup. Longest common subsequence. So consider a pair of strings. And we can ask the following question. If we don't worry about things being consecutive only in a particular order, what is the longest substring that we can find that's common to both of these strings? For example, they both contain a common string of length 1, just the string A, right? Or in fact the string D, right? Or the string T. Okay, so we know there's at least a common substring of length 1. Is there a substring of length 2? Yeah, this contains an AB, this contains an AB. Okay, this contains an ABD, this contains an ABD, so we've got a common substring of length 3. So what is the longest common substring we can find between these two? And it takes some investigating visually. And you know, I might say, well, there's an A and a B and a D and an E and a G, and there's a T and an A and an E. So there's a common substring of length 8. But there could be a longer one. It might be that if I don't start right here, but I were to start with this A matching that A, that I might find a longer substring. And so there's a lot of possibilities for how to pull substrings out of this, right? And basically, you know, every possible substring from here, if this has 12 characters in it, I could make a substring by including or excluding any of these characters. And there's 2 to the 12th possibilities there. That's 4,096 substrings. Substring's basically a subset, right? Except it's ordered. And same thing down here. So there's a lot of work you would do in trying to sort of exhaustively generate every possible substring and compare them. But we can do this recursively by making the following observation. Well, if both of these end with a character that's not the same, whatever the longest common substring is, it could end with a C, it could end with an E, but it can't end with both a C and an E, right? So one possibility is that it does not end with an E, in which case the E has no impact on the answer. And so we could simply solve the question of what's the longest common substring between these two strings. Okay, and that's a slightly simpler problem because one of our strings is shorter. Or it may be the case that whatever the longest common substring is does not end with a C. Okay, because, you know, C is not contained in this one. And so if it does not end in a C, we can solve the question for these two strings. And so we can phrase the question of LCS of these two strings in terms of looking at the LCS of two sets of other strings, each of which are slightly smaller. And if we have a case where both strings do end with the last character the same, then the largest common substring of these two is exactly 1 plus the length of the longest common substring of those two. Because whatever we find is a common substring between these, we can tack an E on the end, and that's going to be common to both of the original strings. So there we can phrase this as a question of finding the LCS of two strings, each of which are shorter than the original. And you can wire that up into a nice recursive definition, and it's got a base case where one of the strings has a length of 0, the longest common substring is 0 length. And since each of these recursive calls will reduce the length of at least one string, you're constrained as to how many recursive calls you'll make. And eventually your recursion will hit a base case. So that's another example. And there's lots of examples of problems that lend themselves to this kind of recursive analysis. And a lot of them have this structure where if you put in dynamic programming, you'll speed them up. Without dynamic programming, you're basically exploring all these possibilities and recalculating a whole tree of recursion for each one, even if you've done it before. All right, good on that? All right, so let me go back to trees for a bit, and we'll do something fairly light for the last 20 minutes here. I said earlier that we could do something like this. All right, here's an arithmetic expression. And we can turn this into a binary tree pretty easily. When we find something inside parentheses, we basically turn that into a tree. So A plus B, we turn into a tree that looks like this. Here's an A and a B, and the operation we're performing is a plus. And here's a C and a D, and they get added together, so they get an operator which is plus. But then those get multiplied together. So we do a multiplication. Let me make this a plus just so we don't have to worry about orders. And so this tree represents this much of the expression. And to that result, we want to add an E. So we can take an E and then add that to the result of that multiplication. And now this tree represents all of this. And now we want to take this result and multiply by an F. So I'll put an F over here, and we'll give it an operator of multiplication. So constructing this tree from this expression is pretty straightforward. And evaluating this expression requires us to know about parentheses and to come in here and say, okay, A and B get added together, and there's a closed paren, and we're not multiplying yet, we have to add these together, and then we can multiply and so on. We can build this tree pretty easily. And now we can do what's called post-order traversal. So left-right node. And so left-right node, remember we go all the way to the left, and then pop up and go to the right, and then finally explore the root node last. So this tree traverses as AB plus, and then we would traverse the right subtree over here, which will be CD plus, and then we'll do the root node, which is star. And that's the left subtree of this bigger tree. We do the right subtree and then the root node. That's all the left subtree of the original. Then we do the right subtree and we do the root node. So that's the left-right node, or the post-order traversal of this tree. And then I mentioned this was something that's called reverse Polish notation. And I told you that old calculators from Hewlett-Packard used to use RPN for doing arithmetic. So you couldn't say parentheses, right? But you could say AB plus CD plus times E plus F times, and it would calculate this expression. And one of the reasons they did that, I believe, was because it's very easy to evaluate this arithmetically using a stack. So we can make a stack-based calculator. And the stack-based calculator will let us take a postfix expression and evaluate it. All right, so how does this work? Process the expression from left to right as follows. If you have an operand, push it onto the stack. If you have an operator, pop the top two things on the stack, apply your operation, and then push the result. And just keep doing this. So start traversing through your string. If you have an operand, push it on the stack. If you have an operator, pop the top two things from the stack, apply the operation, push the result. So here's our stack, and let's grow in this direction. So the top of stack will be at the bottom. So let's go through our expression. First thing we find is an A, we're going to push that onto the stack. Next thing we find is a B, we'll push that onto the stack. Next thing we find is an operator. So we pop the top two elements from the stack, that's a B and an A. We apply the operation, which is A plus B, and we push that onto the stack. Find an operator C, push that. Find an operator D, push that. Find a plus, pop the top two things from the stack, C and D, apply the operation, push that on the stack. So now our stack contains two things, whatever the value of A plus B was and whatever the value of C plus D was. And you'd actually evaluate these with numbers or you know, whatever values you have. Okay, now we come to an asterisk. It's an operator. What do? Pop the top two things from the stack. So that's C plus D and A plus B. Apply the operation, which is an asterisk, and then push this result onto the stack. So now our stack's going to have one thing on it, which is the value of A plus B times the value of C plus D. Next thing is an operand, push that. Next thing is an operator. So pop the top two values from the stack. That's this thing and E. Apply the operation and push that result on the stack. So now the stack contains A plus B times C plus D plus E. And then finally find an F, push that on a stack, find an asterisk, pop the top two things from the stack, apply the operation, push the result back on the stack. So the stack will now contain one thing, which is the value of A plus B times C plus D plus E multiplied by F. So at the end of the expression, the final answer is the thing on the stack. So if you do this with numbers, so 2 plus 3 times 4 plus 5. Well, in postfix notation, this looks like 2, 3 plus 4, 5 plus n times. So push the 2, push the 3, get to the plus, pop those off, add them together. 2 plus 3 is 5, that goes on the stack. Push the 4, push the 5, get to the plus sign, pop off the top two operators, 4 and 5, top two operands, apply the plus, 4 plus 5 is 9, that goes on the stack. Get to the star, pop off the top two entries, that's 5 and 9, multiply them, that's 45, push that on the stack. We're at the end of the expression. The thing on the stack is the result of your calculation, which is just 5 times 9, 45. But we don't have to worry about parentheses or anything like that. It's a stack-based calculator. It's another thing stacks are good for.
So how does it handle multi-digit numbers? Do you just press enter after every number? Or how does that work?
Yeah, so on the old HP calculators, there's an enter button.
After
You type your first number, hit enter, type your second number, hit enter, and then hit the operand. But if we're parsing this ourselves, right, we find the operands and we just take the strings up to that point and so on and so forth. Yeah.
If it's first in, last out, how does it handle subtraction when it pops for 2?
So that's why I changed my subtraction to an addition. So if you want to do 4 minus 5 in RPN, that looks like 4, 5 minus. So the 4 would get pushed, the 5 would get pushed, and then when you see the minus, you would pop off the last 2 and just subtract the thing you popped second from, pop off the thing you popped first from the thing you pop second. You just have to be careful of the order. But it's basically pop, you know, into temporary variables and then do your operation on those. So a long time ago, I think it was like 1992, I was writing a simulator for the cell matrix work that I do, and I was writing it in C, and I wanted a way to be able to enter Boolean expressions. So I could make, you know, something like north equals south and west, or not east. And I didn't want to deal with parsing all of that. I was in a rush. I was between classes or something. And so I decided I would just put this in RPN, right? I would actually enter this as north equals south, west, and east, negate, and then or. And then I'd like change it around to take algebraic notation when I had more time, right? That was like 28 years ago, and I still haven't changed it to algebraic notation. So I have this system out there with software that people have used, and they've done their graduate studies and so on. You always got to put your truth table Boolean expressions in this reverse Polish notation, just because it was easy to code using a stack-based analysis. And I didn't feel like doing a tree traversal, I guess, for 28 years. So it's a good trick to know. So how would you make a parser that would let you type in something like, I don't know, 25, 45 plus 13, 12 plus multiply. Right, something that would let you take in strings like that, or maybe, you know, put spaces in between here. And this should understand that you're taking 25 and 45 and pushing them on the stack as two-digit numbers, and then adding them, and then so on and so forth. And you're just given a string containing that stuff. Right? Could you write a parser that would evaluate this expression using a stack-based calculator? It might not be easy, but you could probably do it, right? And maybe scanf would help you, maybe not. But we don't need scanf, right? Scanf is just a function written in C. We know C. So I mean, you could start at the beginning, and you could look at each character until you get to a space or an operator, or, you know, the end of your string, your new line, or your null terminator, or whatever. And when you get to one of these, let's say this was, you know, character 0, 1, 2, well, since character 2 was my delimiter, I want to take the first two characters from my string and copy that into some temporary car array and set a null terminator after the last one. Well, that's at index 2, right? And so I could make a function that maybe takes this string and pulls off everything up to the first space or operator. And I might even have it return a string that is the rest of this. And if I've got that function, and I know that function works, now this is pretty easy, right? I can just pass this string and say, give me the first chunk. I can pass it again and say, give me the next chunk, right? And I can have a flag that tells me, did I find an operator or an operand? And if I find an operand, then I go ahead and I take the last two numbers that I got. Well, I can take this string and I can certainly run that through scanf. If I know it's supposed to be an integer, scanf will turn it into an int for me. And if it's something like a plus or a star, that's just a piece of information I use to say, should I add or subtract or multiply or divide the last two numbers that I converted. And you make a stack package that'll let you push things. And you're only pushing numbers, so you can make it an integer stack if you want. and you're in business. Well, if you can do that, you got a good start on, you know, writing a compiler or writing an interpreter, something like MATLAB that lets you type in expressions and it evaluates them on the fly. And one of the biggest challenges in programming, I find, is getting people to believe that, like, it really is this simple. That there's no magic language you have to learn to say if somebody says, you know, x17 equals a plus b. You don't have to learn some magic language or some object-oriented concept or some library or something like that to be able to do something with this expression, right? You can take this and you can break it apart as strings, you know, and you can find this by looking for the equal sign, which you do by checking each character to see if it's an equal sign. And I want to save this value in something that's going to be called x17. I don't know, you could make a parallel array where you have an array of names and an array of values, and in here I might put x17 and I might put the value of that variable. Or I could use a hash if I wanted to be fancier. Or I could have an array of structures where each element has a variable name and a value, right? There's all these different ways you can do it, and it's like they all work. And there's no one magic way that you have to do this. Okay, now later courses or on the job, that all changes. It's like you have to use variables that start with the letter Q today because it's Thursday, you know. But, you know, if you're just writing code, it's really just a matter of, like, what do I want it to do? Okay, it's kind of like Minecraft. You know, you want a house and you've got a bunch of wheat. You can build your house out of wheat if you want. Who cares? It's like whatever gets you there. And C is really just like, you know, it's like a mini version of Minecraft. We've got instructions and ifs and variables and arithmetic and things like this, and if you can put them together in a way that does what you need, you can do that. It's totally legal. And, you know, it'll work well. So yeah, we learn a lot of things, and we're learning fancy data structures in this course, and we'll learn all about object-oriented programming in 223. And those are good things. They help you be more efficient. They help you produce code that's easier for other people to read and maintain, and you know, lends itself to sharing and so on and so forth. But fundamentally, I want you to keep in mind this idea that, like, there really isn't any magic here. Right? If you know C or if you know assembly language, right, you can do anything you can do with these other languages, these other environments, these other constructs, right? It's just a question of how it gets done. All right. Where are we going next? So I think Monday I'm going to start talking about tries. And let me just give you a preview of what a try looks like. So here's an example of a try. So each of these is a node in a very, very wide tree. In this particular case, each node is going to have 27 children. One for the letter A through Z, and one for something we call end of string. And so we'll have one root node, and that node can have up to 27 children, and each of those nodes can have up to 27 children. This thing will suck up memory really quickly. Okay, because you got lots of pointers. But we can store words composed of uppercase letters in this structure, and we can access them almost with order 1 efficiency. It's actually going to be order however many letters are in the word. But if you imagine that all the words you might store have 16 or fewer characters, You can put as many words in this structure as you want, and it will never take more than 16 operations to get a word out. So effectively an order 1 storage and retrieval system, kind of like a hash, except it works perfectly. There's no collisions. So we'll go through the basic structure of a try, and then I'll pass out these to groups of 2 or 3 people each, and we'll work as a class manipulating the structure, putting words into it, looking for words, and making changes to the structure. And tries are just like a really fun structure to work with because they're so memory intensive. There's really nothing subtle going on. And it's fun to work with things that are sort of that straightforward. So we'll play around with that on Monday, and then we're going to go on, we're going to start talking about sorting and searching. And that'll be the bulk of what we do next week. All right, cool. I will see you next time.